All right, here we have chapter 2, section 7, last section of the chapter. So now we're going to talk about how all of this radiation and this radioisotopes applies to medicine. So nuclear radiation, remember, can be those high energy particles. So the alpha, beta, gamma, right? Well, really alpha, beta. The high energy rays are the gamma rays or X-rays, right? The rays have no mass, whereas the particles do have a mass. So remember, it can be either or. So we use these in medical imaging, and there are some that will go all over the body, and there are some that will be picked up by certain organs, like iodine is going to be picked up by the thyroid. And so you can actually target particular tissues, and you can use it to create an image. So sometimes it's on a photographic plate like x-rays, or sometimes it's detected by scanning the body, and that's pretty much all the other ones, right? So we can use it to detect, and we can also use it to treat. If you're detecting, you want to expose those patients to the littlest amount of radiation possible for the shortest amount of time. So either you're going to use it to diagnose or to treat, but especially in diagnosing, you're going to give them the smallest amount possible. And so we call that a tracer. It's a little bit of radioisotope and it has a really short half-life. And so we call that a tracer. For example, the Tectanium-99, that's the one that we were talking about before, and it's a tracer because you don't need a whole lot of it, and it's cleared relatively quickly. And so we can use this to actually diagnose blood flow in the lungs. This is an example of two of the images that you get back. This is this one is a normal patient. You can see that the lungs look all about the same color. So they're getting about the same amount of the tracer. But if you look at this patient here, there are some gaps, right? And in those gaps, you probably have some kind of blockage of the blood flow in the lungs. Maybe there's an infection there, depends on what else you know about the patient. But that part of the lungs is not getting oxygen, is not getting blood. And so it's a good way to pinpoint where things are happening in the body. So this is what we call a cold spot. It did not pick up the tracer. So did not pick up tracer. TR. Ooh. Okay. So this is the same concept can be used if you give a tracer that is being picked up too much. A lot of times you do this with rapidly dividing cancer cells. So like with a PET scan, you give a radioactive isotope, and the body in general will pick up some of it, but those cells that divide very, very, very rapidly are going to pick up extra tracer. And so those show up as hot spots. So those would show up really, really bright, whereas the rest of the body would be kind of muted. It would be light. So you can use this idea that some elements are picked up by certain parts of the body. Thyroid cancer is one of them. So you can use iodine-131, it emits beta particles, as either a tracer or as a treatment. So if you use it as a tracer, you're only using a little bit. But if you use it as a drug to treat, to destroy the cancer, you're going to use 1,000 times more of that same iodine-131 to actually kill the cells. Now, the question is, we talked about this last time. Cancer cells are rapidly dividing, so they're going to get the effects of radiation or chemotherapy or whatever it is more because they're replicating more. Why? Well, ionizing radiation, remember, hits electrons in cells, and it hurts them. And one of the places where it hurts them the most is in their DNA, in their genetic material. So every time the cell divides, the DNA gets exposed. And so that exposure and then ionization, where those electrons are stripped off, actually destroys the DNA. So these cells, their DNA is destroyed at a much higher rate than all the other cells. Then if you know it's thyroid cancer, if you make sure that the radioactive treatment is based on iodine, then you know that the thyroid is the only organ that's going to pick it up. And so you can even more direct that treatment to the right place and to the right cancer's tissue. So it's a good way to, even though we're putting something harmful in the body, we're trying to direct it to that one location where cancer is actually present. So there's two ways that you can, well, there's more than two ways. The radioactive iodine you can actually put in intravenously, but there are two other ways that you can treat patients with radioisotopes. You can do an external beam where the gamma radiation is generated from cobalt-60, and the rays are actually directed at wherever the tumor is in the patient's body to destroy the tissue. Or you can actually implant one of these they're called titanium seeds, and they contain radioisotopes inside of them, and you actually basically cut open the patient and insert it inside the tumor. So the tumor now surrounds this titanium seed and gets the bulk of the radiation and therefore dies. So there are a couple of different ways that you can do that. So I alluded to this in the very beginning, positron emission tomography. So that's a PET scan. A PET scan is used to identify functional abnormalities, like something is overactive or underactive, something like that. And so what you have is a radioisotope, and in this case, a lot of times what they use is fluorine-18, and it has a short half-life, 110 minutes, and half of it's gone, right? So this fluorine isotope will emit a positron, and it's going to decay into oxygen-18. So when it decays into oxygen-18, that oxygen-18 is fine for your body. It's just the fluorine-18 that's not. So it emits that positron. Remember that positron is the same mass of an electron, but a different charge. It's positive. So the positron comes into contact with the electron, and when that happens, it emits a gamma radiation, and that's what's detected by the scanner, right? So this is used a lot of times in the brain to look for maybe like a tumor inside of the brain, that kind of thing. But you have to have some kind of radioactive isotope so that you have something to detect. All right, so that is the end. You got your little study guide at the end, but what we're gonna do is go and do a few quick problems on this practical application. So we're gonna do the odd numbers. So we got 2.41. All right, because calcium is an element in the bone, why do you think it might be useful to use radioactive calcium-47 in the diagnosis and treatment of bone disorders? So if you give a patient calcium-47, where's that going to go in the body? Well, the body is going to not see a difference between normal calcium and calcium-47. So the calcium-47 is incorporated into patient bones. So then you'll be able to visualize maybe if something's going wrong in the bone, or to actually treat it. And so calcium, because it's a component of bones, the body doesn't know the difference, it puts it in the bones. And then you can look at maybe it should accumulate at this much, or it shouldn't, whatever it is, you can see if something's going wrong. All right, let's see. Chromium-51 is used in imaging red blood cells and has an effective half-life of 27 days. If a dose with an activity of 40 microcuries, that's with the little, it's the U with the little extra long thing, right, is given to a patient, how long will it take for the patient to have less than 5 microcuries present? Okay. So this one, you actually have to kind of do this. What are you starting with? You're starting with 40 microcuries. And I want to get to the point where I'm down to 5. So what I have to do is keep doing half-lives and see what happens. So if I do one half-life, so here's my first half-life, that's going to be 27 days. I'm going to take 40, divide by 2, I get 20 microcuries. Am I at 5? Not yet, I gotta keep going. So I'm going to do a second half-life. That second half-life is another 27 days. So now I'm up to 54 days. Okay? So half is 10 microcuries. We're still not to 5. So we got to do another half-life. So here's my third half-life. That's another, third half-life. That's another 27 days. So 54 plus 27 gives me 81 days. 10 divided by 2, because it's a half-life, is 5. So 5 microcuries after 81 days. So how many half-lives did it go? How long will it take? It took 3 half-lives, and 3 half-lives in this is 81 days. So the answer is equal to 81 days. Okay. All right. Now, oh, is that our last one? That's our last one. Oh, so sad. All right. Well, y'all have a good rest of your evening, morning, whatever it is when you're watching.